Hi everyone, welcome to video number 2 of Physics Mechanics. In video number 1, we learned about kinematics, and in this video we will dig even deeper and learn about kinematics in 2 dimensions. We will be using the 5 kinematic equations from video number 1 in this video, so here they are in case you need to review them. We will begin our journey of 2D kinematics by first learning about vectors. A vector is an arrow with a magnitude and a direction. Here's an example of a vector. It has a magnitude of 2 and a direction of 60 degrees north of east. North of east means that you start with the line going east. In this diagram, it's represented by the black line, and you go 60 degrees up or north. Here are some more examples. So the green vector is the same as the one you just saw, except this time you also see a second way that you can express the direction, 30 degrees east of north. So we basically swapped north and east, and the new angle is 90 degrees minus the old angle. This process can be applied to any vector. So let's take a look at the red vector. It has a magnitude of 1, so it's half as long as the green vector, and the direction is 45 degrees south of west or 45 degrees west of south. The blue vector has a magnitude of 2, so it has the same length as the green vector, and its direction is 70 degrees south of east or 20 degrees east of south. You can turn a vector into component form. The x component is m times cosine of the angle north of east, and the y component is the magnitude times sine of the angle north of east. So let's turn the green vector that we just saw into component form. Its x component is 2, which is the magnitude, times cosine of 60 degrees, which is 1. And the y component is 2 times sine 60 degrees, which is root 3 or approximately 1.73. The red vector is a little more difficult because the angle is not expressed in north of east, so we have to turn it into north of east. So we just start with the line going east, and we go up and around in a circle until we get to the red vector, and then the angle that we travel is the angle north of east. So in this diagram, you can see that the angle north of east is 180 plus 45, or just 225. So the x component of the red vector is 1 times cosine 225, which is negative root 2 over 2, or approximately negative 0.71. And the y component is the same thing. You can also turn a vector back into magnitude and direction form. The magnitude is the square root of x squared plus y squared. That's just the Pythagorean theorem. And the direction north of east is arctan of y over x. And if the vector lies in quadrant 2 or 3, you must also add 180 degrees. So let's turn the green vector back into magnitude and direction form. So we know what the x and y component are. So its magnitude is just the square root of 1 squared plus root 3 squared, which is 2. And the direction is arctan of root 3 over 1, which is 60 degrees. And the red vector has a magnitude of 1 by the Pythagorean theorem, and the direction is arctan of negative root 2 over 2 divided by negative root 2 over 2, and then plus 180 degrees because the red vector lies in quadrant 3. So it is 225 degrees. To add two vectors together, you add their x and y components. So by adding them, you can use the tail to tip method. The tail of a vector is the side without the arrow, and the tip is the side with the arrow. So if you place the tail of one vector onto the tip of another vector without changing their magnitude or direction, then the resulting vector is the sum of the two vectors. And you just add their x and y components. So this orange vector has an x component of 4, and the purple one has an x component of -1. So the resultant vector, if you add them together, will have an x component of 3. And in a similar way, the y component of the resultant vector will have a magnitude of 7. Now we're getting into relative motion, which involves having several velocities acting on an object and finding the overall velocity when all of those velocities act together. This can be done using vectors. And the reason why relative motion is called relative motion is because the velocity of an object is sometimes stated relative to the velocity of another object. Here's an example relative motion problem. A boat travels across a 100-meter wide river at a velocity of 4 meters per second relative to the water. What that means is the displacement between a certain particle of water and the boat is increasing at a rate of 4 meters per second. So if you chose just a certain particle of water, say the particle of water directly underneath the boat at its initial position, then the displacement between that particle of water and the boat is increasing at a rate of 4 meters per second, accounting for the fact that both the water and the boat will be flowing upstream. The water flows upstream at a velocity of 3 meters per second. What is the overall velocity of the boat, and how far upstream has the boat traveled when it reaches the other end of the river? So for part A, we need to draw a vector diagram. A black dot is going to represent the initial position of the boat, and the boat has a velocity of 4 meters per second crossing the river. And we're going to say that going right means crossing the river. The water velocity is 3 meters per second up because the water is going upstream. And the resultant velocity is obtained by adding the boat and water velocity vectors. So it has an x component of 4 meters per second, a y component of 3 meters per second, and a magnitude of root 4 squared plus 3 squared, which is 5 meters per second. And that is the answer to part A. For part B, we use this formula, d equals w times vu over vo, where d is the distance upstream, w is the width of the river, vu is the velocity upstream, and vo is the velocity of the object. So plugging in the values that we already know, we're going to get that d is equal to 75 meters. So if you had gone 4 meters right, then you would have gone 3 meters up. If you had gone 100 meters right, then you would have gone 75 meters up. And remember that 100 is the width of the river. Here's another example problem. A motorboat travels across a 100-meter wide river at a velocity of 13 meters per second relative to the water. The water flows upstream at a velocity of 5 meters per second. The captain of the motorboat doesn't want to go upstream any amount, so he travels in a direction such that the boat crosses the river without moving upstream. What is the overall velocity of the boat, and how long does it take to travel across the river? So this time the vector diagram is going to look slightly different. The water velocity is still going up. However, this time, since the captain doesn't want to go upstream any amount, the resultant velocity, not the boat velocity, is going to be the velocity that is going to the right. So the motorboat velocity has to go slightly down such that its y component is -5 in order to counter the effect of the water velocity. So the motorboat velocity has an x component of the square root of 13 squared minus -5 squared, which is 12 meters per second. And the y component, as we already know, should be -5 meters per second. The resultant velocity, therefore, has an x component of 12 plus 0, or just 12, and a y component of 0. And the magnitude is 12, which is the answer to part A. For part B, we just use a kinematic equation. So the time it takes to cross the river is 100 meters over the velocity with the velocity at which the motorboat crosses the river, which is 12. So the time it takes is 8.33 seconds. Now we're getting into projectile motion. If you launch an object into the air, what path will it take? Where will it land? Those questions can be answered with projectile motion. To understand how projectile motion works, we're going to explore a PhET simulation, which I'll link down below in the description. So first we click on vectors, and then we uncheck air resistance, click on components, and show the velocity vectors. And now we can launch the projectile. The important thing to notice was that the x component velocity vector did not change throughout, and the y component velocity vector changed at a constant rate due to acceleration due to gravity. So this is a very important part of projectile motion, and now that we know it, we can dive into some practice problems. Most projectile motion problems will ask you to determine the horizontal distance the projectile travels. To calculate that, first you calculate the amount of time the projectile is in the air, and then multiply it by the horizontal velocity. So here's an example problem. A projectile is launched with a velocity of 10 meters per second at an angle of 30 degrees from the ground. How far does the projectile land from its starting point? Well, to determine the time, first you need to know what the x and y velocities are. The x velocity is 10 times cosine of 30 degrees, which is approximately 8.66 meters per second. The y velocity is 10 times sine of 30 degrees, which is 5 meters per second. And we need to use the y velocity to determine the time. And if you remember in video number 1, if you throw an object upwards, when it comes back to its initial position and it's going downwards, its velocity is negative the initial velocity. So therefore, the final y velocity is negative 5 meters per second. Now we can use the third kinematic equation to solve for time. So we plug in all the values we know, and we get that time is equal to 1.02 seconds. And now we can multiply this by the horizontal velocity, which is 8.66 meters per second, and we get that delta x is equal to 8.84 meters. Here's another example problem. A projectile is launched from the top of a 20-meter tall building at an angle of 45 degrees from the ground and a velocity of 15 meters per second. How far from the base of the building does the projectile land? This time it's more difficult to determine the amount of time the projectile is in the air, but either way what we do is first we need the initial velocities. So in this case, they're both 10.61 meters per second. And to determine how long the projectile is in the air, we need to use the fourth kinematic equation. So we plug in all the values and we need to solve for t. And this is kind of tedious because we have a quadratic equation and the coefficients aren't nice. So when we get to practice problems, I'm not going to give you any practice problems that require the use of the quadratic formula. For this problem, I'll just tell you that t is equal to 3.37 seconds. And now we multiply 3.37 seconds by the horizontal velocity, which is 10.61 meters per second. And we get the final answer is 35.79 meters. Now I have one relative motion and one projectile motion practice problem for you. And both of these problems add a small twist to the example problems you've seen to keep them fun and non-repetitive. Here's the relative motion practice problem. And you'll notice that this time there are 3 velocity vectors. However, you can still use the tail to tip method and add them together, just like we did for the problems where there were 2 velocity vectors. If you want to give this problem a try, then pause here. The solution will come in 3, 2, 1. So here is the vector diagram, and the wind velocity has an x component of negative 1 meters per second and a y component of 1 meter per second. The resultant velocity, which is obtained by adding the 3 velocity vectors together, has an x component of 179 meters per second and a y component of 1 meter per second. And the magnitude is 179.003 meters per second. For part B, we only care about the x component of the resultant velocity since we're trying to find how long it takes to travel a certain distance east. So we use the first kinematic equation. 1,000 meters is equal to 179 times t, and we get that t is 5.59 seconds. Here's the projectile motion practice problem. The process for solving this problem is similar to the example problems we've seen. This time you want to solve for the amount of time the projectile is in the air before it reaches the wall, and then you want to solve for the height of the projectile at that time. If you want to give this problem a try, pause here. The solution will come in 3, 2, 1. So first, the initial velocities are, for x, 50 times cosine 60 degrees, which is 25 meters per second, and for y, 50 times sine of 60 degrees, which is approximately 43.3 meters per second. So how long is the projectile in the air before it reaches the wall? Well, we know that it has to travel 50 meters horizontally, and that the horizontal velocity is 25 meters per second. So overall, it's in the air for 2 seconds before reaching the wall. And now we need to use the fourth kinematic equation with the vertical velocity to solve for the height of the projectile after 2 seconds. So we plug in all the values, and we get that delta x is 67 meters. And since 67 is greater than 60, the projectile travels high enough to go over the wall. So I hope this video was super helpful. Here's a quick recap of the topics. We started with vectors, and the important concepts were converting a vector into component or magnitude and direction form and adding vectors. And then we learned about relative motion, which was essentially just applying vectors. And then we finished with projectile motion. And the important things to remember are the horizontal velocity is always constant. And to solve a problem, you usually first need to determine the amount of time the projectile is in the air. Thanks for watching. I'll see you in video number 3.